Today we're talking about morphology. So first, what is morphology and why should we care about it? So morphology is the study of morphemes, and morphemes are the smallest unit of language that carries meaning. So books has two morphemes, book and s. So book tells you that you're talking about something related to books, and s tells you that you're talking about more than one book. Unladylike has three morphemes: one, un; two, lady; three, like. Un tells you that it's not ladylike. Like tells you that it's like a lady. You have one word, unladylike. And if we're going to automatically do anything with language, we need to do an analysis at the correct level. And for many languages, that requires us to care about morphology and extract the true meaning out of very complicated words. So there are two broad kinds of morphology. There's derivational morphology and inflectional morphology. So derivational morphology is when you have a new word that is derived from an existing word that somehow changes the meaning. Computer is a word. If you add isation to the end of it, that means that you're taking something that didn't have computers and adding computers. Similarly, appoint, that's a verb. If you have an appointee, however, that's someone who has been appointed. And so oftentimes these derivational morphologies change the part of speech, so going from noun to verb or from verb to noun. Inflectional morphology is more about variations of a word that doesn't change the meaning, but allows the word to fit into its grammatical context. So tense, number, person, these can change words' surface features, but not their underlying meaning. So for example, in English, the pizza guy comes at noon. Comes is an inflected form of come. So there are a lot of words that we use when we talk about morphology. So root is common to a set of derived or inflected forms, and stem is a root of a word together with any of its derivational affixes. So you keep as much as you need to preserve its meaning. Affix are bound morphemes that come after or within a root or stem. So this is something that is bound or connected to another morpheme within a word, somehow changes the meaning. Clitics are morphemes that function like a word but doesn't appear on its own. So I've in I've means have, but it never appears on its own. It has to be glued together with another word. So some examples, some extreme examples of this are Rechtsschutzversicherungsgesellschaften. So this is a legal protection insurance policy. Many morphemes put together in order to create this rather complex concept. And similarly, Turkish, another language with a rich morphology, can create words like this. I won't try to pronounce it. That refer to behaving as if you are among those whom we would not cause to become civilized. Some languages have richer morphologies than others, so Spanish has a lot of conjugations. English, for some words, does have some inflectional morphology, so I eat, he eats, they're eating, I ate, showing different tenses and number. Whereas other languages like Chinese have no inflection whatsoever. And so that makes Chinese relatively easy in terms of morphology. You don't have to do anything. English is fairly simple, and oftentimes you can get around not using morphology, but morphology can be productive even in English. So faxed, Skyped, Britted, these are words that have been produced from existing words and thus increase the richness of our language. So how do we deal with morphology in a computational linguistics course? So we're going to be talking about two tools that allow us to deal with morphology. So the first is a simple problem. We want to know whether a word is in a language or not. And for English, one approach you could do is just make a really long list. It's harder for other languages and in fact impossible for other languages where you can build words together on the fly and it happens all the time. But even for English, just building a list isn't necessarily the most elegant or practical solution, because you're going to miss out on the derivations, the inflections, and you're going to generate a lot more work for yourself. So maybe we can do something a little more elegant. And what we're going to do in this course is apply a tool called a finite state automaton. Okay, so what's an FSA, or finite state automaton? So it's defined by the following things. So first, you have an alphabet. So these are the letters that appear in your language, and you define a set of states. And so typically, we will represent an FSA by diagrams that look like the thing you see on the left. So the states are these circles, and some of these states are designated as the start state, and some of these states are designated as the final state. So you only have one start state, you can have any number of accept states. And edges move you from one state to another. And so how do you know which state you move to at a given time? It's based on something that you've observed from your vocabulary. So, for example, you start in the start state Q1, then you see an A, and so you look for the line that has the arrow going out of Q1. That has an A on it. You go to Q2, and as long as you're in Q2, that means you're in a string that belongs in your language. And so this is an FSA that tells you, I like strings that end with A. And as long as you have a string that ends with A, that will be a part of your language. Any string that doesn't end in A will not be part of your language. One thing to look out for in FSAs is that every state will have an edge going out of it corresponding to everything in your vocabulary. So if you're in Q2, there are two things in your vocabulary, A or B. If you're in A, if you see an A, then you stay in Q2. If you see a B, you go to Q1. Whereas with Q1, if you see an A, you go to Q2, and if you see a B, you stay in Q1. Okay, so let's go through some examples. What is the FSA that tells you if you have a binary string? So as long as you see a 0 or a 1, that means you're in a binary string. If you ever see a 2, that means it's not a binary string. So what about binary strings of even length? At first, you don't have a string of even length. If you see a 1, then you don't have a string of even length. Yet you have a string of length 1. But if you see either a 1 or 0, then you're in a string of even length. But if you have a string of even length, and if you see a 1 or a 0, then you no longer have a string of even length. I did something a little bit pedantic here. If you have a string that starts with leading zeros, they're not actually part of the string. So as long as you see zeros, that actually doesn't start your string. If you have an automaton that accepts strings of odd length, that looks very similar, except you just flip which is your accept state from Q3 to Q2. Okay, so let's now do a more complicated example. Let's say that you wanted to accept the language of questioning cows. And so every string must begin with an M, and every string must end with a question mark. And there must be an O in between, but there can be any number of O's in between the M and the question mark. So, think for a second about how you would create a FSA that accepts this language using the alphabet M, question mark, and O. Okay, so at this point you should have an idea of what that automaton should look like. Pause the video if you don't. So we first start not being in an element of the string. One thing that we'll use is we'll use a garbage state, Q5. If we ever get something that shows that we're not in a properly formed string, we go to this garbage state Q5, and no matter what happens, we just stay there. So we start in Q1. We see an M, we go to Q2. If we see anything other than an O, we go to the garbage state. Once we see an O, then we go to Q3, and that means that we've seen one O. We can see any number of additional O's, and we stay in Q3. If we see an M, that means we're in the garbage state. But if we see a question mark, that means we're in a valid string, and we're done. And you can do a lot of stuff with FSAs. We won't talk about them right now, but we'll see plenty of examples in class, and there are examples in the book. But you can take intersections, differences, complements, reversals, concatenation, and it's closed under all of these operations. Okay, but we've thus far been talking about this abstract FSA. How do you actually apply it to languages? So we can recognize languages, and we can even recognize real natural languages. And we need to do that for things like spell checkers, language identification, or speech synthesis. And so suppose that you have a finite state automaton that can detect English stems, one for nouns, one for verbs, adjectives, etc. You want to also recognize inflected forms. So you can do that with union and concatenation operations. So here's an example with nouns. So let's say that we only have two nouns in our vocabulary, dog and cat. You can see how this generalizes to more possibilities. And now let's say, so this is an FSA that detects nouns, but let's say that we also wanted to detect plural forms. So you just add on an additional state like this. The first half of the FSA detects the noun, the second half detects the plural forms. It gets a little bit complicated because not all plurals are formed by just adding an S. You can read about that in the book, and we'll talk about it in class. And it's also the subject of the first homework. But we'll need a little bit more complicated machinery in order to handle both nouns and verbs at the same time. And so in order to handle that, we're going to make our FSAs non-deterministic. And so what this non-determinism means is that, one, we can have empty edges between states. And so this basically is a free pass to go from one state to another. You don't necessarily need to observe any associated element in your alphabet. And so this creates multiple universes, as it were, for strings to follow. And so as long as you can go through any path in your FSA that leads to an accept state, then it's part of the language. And so the book uses epsilon to represent empty input or output, and I'll use just a blank edge instead. So if we want to add on verb affixes like ing or ed, we can create a larger automaton that looks something like this. So you have the verb leading to the state Q8, so that means it's a valid verb, and then there are two endings you can add on after that. So now non-determinism comes in. We have that noun and plural FSA that we had before, so that's state Q14 to Q20, and we have the verbs Q2 to Q13, but we don't know whether a word is a verb or a noun. So we add in this non-deterministic start that allows us to choose either way. So we have an empty transition between Q1 and Q2 saying you can be a verb if you want. We have a non-deterministic transition from Q1 to Q14. You can be a noun if you want. And if either of those leads to an accept state after seeing some input, then we say that that's part of our language. And so this is sort of a schematic overlay that shows you what's going on in each part of this FSA. You have the non-deterministic start, you have verb and noun bases, and then the affixes that we allow. Thus far, we've just been dealing about a binary yes or no answer. Is this string in our language or not? And so what we're going to do to make this a little more versatile is we're going to change from using FSAs to something called a finite state transducer. And so instead of just giving a binary output, is this a string in our language or not, we're going to give arbitrary output. So for example, in the homework, you'll be creating a finite state transducer that can give you inflected forms of words. So for example, if you have the word go, but you want the third person past tense of that word, you can throw that into a finite state transducer. And so all that we have to do to turn finite state automata into finite state transducers is for the edges, add an additional output for each edge. So this is clear with an example. So let's say that we wanted to turn the FSA that detected the language of inquisitive cows into the language of emphatic sheep. So the language of emphatic sheep is that those strings start with B, have any number of A's, but at least one of them, and end with an exclamation mark. So you start in a state, Q1. If you see an M, you output a B. If you see an O, you output an A. And move to Q3. And if you see an O, you output an A as long as you're in Q3, and you can do that as many times as you want. And then finally, in Q3, if you see a question mark, you output an exclamation mark, and that's a valid string. And if you ever end up in the garbage state Q5, you output nothing. So this is how you turn inquisitive cows into emphatic sheep. So we have now talked about what you need in order to get started doing morphological parsing. And this is the subject of the first real homework. It will take inputs like cat plus noun plus plural and produce output like cats. So read chapter 3.5 very carefully, read the assignment carefully. We'll talk about it in class and get you started doing morphological analysis. And remember, we'll have a quiz in class as well. It won't be as easy as the first quiz. I'll actually ask you something about the content of this lecture. And we'll go through any questions you have about the assignment, and we'll do an example about how you convert from English characters into the runes used in Tolkien's The Hobbit and Lord of the Rings. So, looking forward to that, and I'll see you in class.